let's talk about basis functions. So you have seen me throwing around basis functions and basically pulling them out of thin air. Now we will actually see how you derive these functions and what properties we want from basis functions, and and the definition of the basis functions. So let's start by just looking at them graphically. So we have on this left hand side here, we have linear basis functions. So we have phi1 and phi2 here, and we can already see some properties of these basis functions. So they're in this general coordinate system x1 to x2. So what we can say about x1 and x2, we can call these nodes. So we have two nodes in x1 and one in x2. And if you look at the first basis function, this one here, the property of any basis function really is that it's supposed to be have the value 1 in its node. So its node, the node which is attached to the number which is attached to the basis function here, is corresponding to this node here. So when we say its node, we mean the node 1. So this one here, x1. That's supposed to be 1 when we are at x1, and it's supposed to be 0 in all other nodes. So we have only x2 here, but if we extend this window to x3, x4, x5, whatever, then all of these nodes are supposed to be 0. So this thing is just going down, and it stays down for the rest of our mesh. And the same thing goes for phi2. So phi2, its node lives in x2, because that's the same number, and it's supposed to be 1 in that node and 0 in all other nodes. So we might have negative nodes over here, or negative x values over here, and this thing is going to be 0 there as well. These are also called hat functions because they look like hats if you draw them out. They're linear. And the same thing goes for higher order functions. So we have this thing here, which is a quadratic function, and it too, so phi1 is this one here. It's 1 in its own node, phi1, x1, and it's 0 in the other node. So if you look at the scale here, we have 0 values here. So this is 0 and this is 0. So it actually becomes negative. It takes negative values between x2 and x3. But at x2 and x3, this guy is 0. Let's take a look at phi2. Well, it's 0 in x1, it's 1 in x2 in its own node, and it's again 0 in x3. And the same thing goes for the third one. So what we can say is that there's a rule that governs this. We define this rule, so we should really type colon here. So this is the definition of these basis functions. And what we're saying is, okay, index j here denotes the number of the basis functions, and index I here denotes the number of the actual node of the x position. And we're saying that, all right, the value of phi is 1 if I is equal to j. So if we are in the same node, so if these two numbers are the same, so if phi1 for x1, it's going to be 1. Phi1 for x2 is going to be 0. Phi1 for x anything other than 1, it's going to be 0. That's what we're saying here. And this definition is general enough to explain how this works for any function, any basis functions. And what I can say about this more is that the approximation, if you look at that, so basically we're saying that some function of x is defined by the sum of the basis functions I times u I. So we're sort of weighting these coefficients or these values here using our basis functions. And what is interesting that this basis function is of course a function of x, right? Like so. And this u values can be, well, basically any number. We don't really care about it. But what we're saying is that we're multiplying these functions with ui such that they will never change the value of ui. So what I mean is that for any x, if I evaluate x at this point here for both of these functions, and I take a look at the value of ui, we have a property called the partition of unity. That means that this weight here is always going to be summed to 1. So if we just if you get rid of ui here, if we just do it like this, then we can always say that for any x, this thing will be 1. It's always going to be summed to 1 for any value of x. That's the partition of unity property. So I can type that here. So we have the definition of basis functions there, and we have the partition of unity, and that's how actually our approximation works. It's not being scaled in any way. So yeah, I can actually change this to some other function g of x, let's say, just to make things very valid. Alright, so once we get this definition out of the way and we have seen this graphically, so let's derive a basis function for for a linear function. So linear basis functions. So I'm gonna copy paste stuff. So what we're saying that we have to make the ansatz. So this is basically we're saying that the basis function is following a linear polynomial like this. Okay, and using our definition here from 1, we get the following. We get phi1 of x1. So evaluated at x1, this thing is supposed to be c1 plus c2 x1, and then this is going to be 1. And then using again our definition here for the other node, which is x2, c1 plus c2 x2 is going to be 0. So additionally to this, we have the following. We have that the second basis functions evaluated at x1 is going to be 0, and the second basis functions evaluated at x2 is of course going to be 1 because j and I are equal. Alright, so of course we can obviously see here that we can now solve for c1 and c2 out of this equation system, and we have our basis function, and we can do it for this separately here. We can solve for c1 and c2, and we have our basis functions phi2. But we can do this more systematic. So this can be expressed as a matrix system, like so. So we look what we have here in front. We have we have 1, what the coefficients before c1 and c2 are. So we will extract c1 and c2 out of this. So we have 1, and we have x1 here, and these are multiplying our c1 and c2. So we have 1 x1, 1 x2. So if we do this matrix multiplication, we will get back this stuff here, and this is of course equal to 1 and 0. So this 1 and 0 comes here, and we're also increasing the indices here. So we're saying that alright, these this first index denotes the first basis function, and the second index of course denotes which coefficient it is, 1 and 2. And over here we have, for this side, we have the same 1 x1, 1 x2, but now it's multiplying, so we're separating these so we don't mix them up. So c1 and c1 and c2 over here are not the same as c1 and c2 over here, so that's why we're calling them different things, because this 2 here, this first index denotes what basis functions they belong to. So in this case we have 1 x1 times c2 1 is equal to 0, again following this, so it's the same stuff, right? Alright, now instead of expressing it this way, you know, using two different equation systems, what we can do is throw this in like so. So we can combine these C1 and C2 into its own matrix. And now we have 1, x1, 1, x2, and this matrix is called A, and then we have our coefficient matrix C here, and we have this thing which we identify. We just put them together next to each other, and we identify this as the identity matrix. Right, so far so good. Now we can solve for this thing. We can solve for C, and then we can insert C back to get our function phi here, which is a vector now. Phi, which is a function of x, of course. So we have 1x multiplying C here. And yeah, if we just look more closely at that, let's expand it just for clarity's sake here. So we have phi 1 and phi 2, which of course are functions of x, both of these. Right, we are taking 1 and x, and we are multiplying that with C1 1 and C1 2, such that we get C1 1 times or plus C1 2 x. So that's our first basis functions, and the second one is of course 1 times C2 1 and x times C2 2. So that's the thing over here, and that's the mathematics behind this. And I shall do this for quadratic basis functions soon, but for now let's jump into the actual MATLAB code. So I'll clear the workspace here, so it's gone, and I'm gonna create these coefficients. I'm gonna create, well, what do I need to create? Well, here I need to create x1 and x2. Yeah, so sims x2, so x1 and x2. So these are my symbolic variables, and now I create this A matrix, which looks like this. We have 1 x1 and 1 x2. So that's that thing. You can suppress that, don't need to see it. Simple enough. And I'm gonna create my identity matrix, which is a built-in function in MATLAB. So I can do I and then the size of the matrix. It's going to be 2 here, so 2 by 2 thing. And then I can define C, or compute C. And now I can show you here how to do this the wrong way, so that I will never see you doing this. So instead of doing something like you would do by hand perhaps, which is to invert A and then multiply that by I, like so, I get the true answer. But notice here that MATLAB doesn't really like this. I mean, it's sort of saying, like, don't be an idiot, don't do this, this is very slow and inefficient, never use this outside of finding out what the inverse of A is for whatever reason. There is never, it's never interesting to compute the inverse and then multiplying it with something else. Instead, we can use the backslash operator. So we do A backslash I in order to get our to solve the equation system. And again, this thing is called ML divide, but it's also can also call this linsolve, because we're solving a linear equation. So if you look at the help for that, we have A, B here. So solves the linear system AX is equal to B using one of these methods. So yeah, I mean, you could do this. It's not the same as backslash operator though, so I just prefer the backslash operator because it's more general. What am I doing? A comma B, A comma A comma I. So, but you can see here that we get the same output. Yeah. So yeah. So let's look at the third method. You can do you can do this thing. You can invert it this way and then multiply by I. Also extremely inefficient because you're just computing the inverse. So this thing here is the same as writing inv A. So don't do this. Bad practice. Stick to good practice. So that's the proper way of doing it. And now I've showed you how not to do it. So you don't need to test yourself. Yeah, just don't don't use any of the other methods. It's not good. Right. All right. So we have our coefficients now here. So now we can create phi, which is just going to be this operation here. So we have 1 and x multiplying c. And that's our basis function. Now we can, of course, simplify this now because it's not simplified. So simplify and get it like this. Now, this is the problem. Well, MATLAB, and it's following, when you use symbolic toolbox or any symbolic operation, be it Wolfram Alpha, Mathematica, MathCAD, whatever, SymPy, whatever, it's always going to use an algorithm which produces the output where the index is, when the lowest number is on the far left side. So this thing is really a difference, and usually if we go from right to left, then this will be a smaller number. So let's say x1 is 0 and x2 is 1. This will be negative. So this whole thing is just inverted, and it's not the same as when we do it on paper, perhaps ourselves. But it's just spitting this out. There's no easy way of redoing this, so it shows something else. So I'm just going to leave it as is. But you can try this out now. So we can set some x1 to something we know. Let's say 0, and x2 to 1. And then we can do subs phi here, and we can see that this produces the known basis functions in the range of 0 to 1. So it works. Yeah, we can actually leave it like this. So good, we have this thing. Now let's plot this. Let me just show you how to make this nice graph I have created here. So what we will do is we're going to create a new figure, and we're going to do fplot phi, so I can actually send in a vector of expressions here, and I'm going to do this from 0 to 1. And actually I'm going to pimp this with a line width of 2. So I'm going to set that to 2, and I'm going to plot this. And I'm getting all sorts of trouble here because I have not well, I have too many unknown variables, x1 and x2, so really I should do I should replace phi with the subs phi here, like so. Okay, I don't really care about these ticks though, so I wanna get rid of these. And now I don't remember the code of doing this. I always forget that. So I'm gonna show you how to do this without looking through the help files and examples and whatnot. There's actually an easier way. So what we can do here is we can open this figure window, so we get it separately like this. And now we can go to this tool here with the edit plot. You can press here somewhere, and we can do open property inspector. So we will get this window here, and here we can take a look at our x sticks. So I'm gonna go ahead and delete everything except 0 and 1, right? And then I'm gonna call this x1, and I'm gonna call this x_2, like so. Whoops, I forgot the x somehow. Come on. Yeah. Now I don't really care about this font either, so I want to change that. I want to change it to something which is more well, kosher in academia, which is actually Times. I don't care about these modern fonts. Times is where it's at. And let's increase the font size because, well, it's too small, so 16. Alright, now we have this y-axis here. Let's get rid of that. We don't want anything other than 0 and 1. So, because this is our values. Alright, so we have this. Good enough, but yeah, really we don't show math using upright, so we want to have font angle here. We want this to be italic. Now I'm okay with this. I can live with this. My OCD is not reacting. What I want to do now is perhaps just show how to do this in code. So I can just right click on this and press show code, and it will generate this function here. I'm not going to use like this stuff. I'm just going to copy this thing, because I see here that there's the font angle, the font name, the font size, the xtick data, and x labels, and all of that stuff, which is important, which I want. I'm just going to copy this and back into here and set it here. Now this thing is using the name axis1, and this is created somewhere, yeah, here. So axis parent, yeah, you don't really need to do that. There's a trick to do this fast. I don't really know why they don't generate this, but you can use GCA. So GCA means get current axis. So it's gonna look at what is the last drawn axis, and it's gonna well, that's what you get in GCA, get current axis. So we're gonna use that, and now if I run this, I'll get bam, the same thing back. Yeah, because there's no way of putting this back into the right hand side here. You could always, that's exactly how I did this. These are pictures. You can always grab this by just copying the output and just paste it as a picture here. So you have always that option. Now I want to actually show the legend here. So I'm gonna show you how to do that. So I can do legend. I can use the legend function, legend, and I can do var phi 1 and var phi 2. And you see, it doesn't really recognize what var phi is, because it only knows about phi. For some reason, doesn't even know that. Let's use the backslash operator here. There we go. Okay. How about var phi? No. So we need a different interpreter. So you have these things called interpreters. They are basically what does this LaTeX stuff. And right now it's just using TeX. It's not using LaTeX. And if you want to use LaTeX, we need to put this in $signs, like so. And it's still not going to work, because we haven't really told it that it should use the interpreter LaTeX. So we need to do that somehow. And the only way of doing it is we need to set this to a handle. So every function in MATLAB is going to spit out a handle. Doesn't really show you here in this help file, but everything spits out an handle. So we can call this HL, and HL is now containing all of the features for this handle here. And the command window is perfect to find out what it contains. So we can show all properties here. And for HL, this legend handle, or object if you want, if you're coming from programming, this is nothing but an object, but MATLAB calls it handles. Yeah, so we have somewhere here, we have interpreter, maybe here. Yeah, and you see the interpreter right now is set to tesh. So we can change that to LaTeX. So what we're going to do is just put a semicolon here and do hl.interpreter, and you can use tab to find this, and set this to LaTeX. We can use the tab here to see what our options are. And bam, we have var phi suddenly. Now, I know there's a lot of work to be done in order to just, change this thing here, but, it's fun, come on. Pimping this stuff is more fun. I can spend like 16 minutes creating this whole thing, and then maybe an hour just to make it nice the way I look. Alright, so we have done this. Let's move on. Let's create another cell and do, well, what we're going to do here. We're going to do quadratic, or quadratic basis functions. Right, so what is the property? So first we make the Ansatz again. It's a German word. There's no better word for English. I mean, in Swedish we have Ansatz, it's the same thing, but English speaking people need to use the German words for reasons. I guess there's so many German mathematicians, and that's why they have defined all of the words. I don't know. Could be. I don't know. So we make the ansatz. So we're saying that this thing is supposed to be a quadratic equation, right? Second order thing. Just as easy as this. All right, and then we use the definition here, this guy, and we create the same thing we have done here, but now we do it for our quadratic little friend here. So I'm gonna copy in. Oops, I'm gonna copy in this thing. So we have this now. So we have phi1 evaluated at x1. It's supposed to be c1 plus c2 x1 plus c3 x1 squared equal to 1. And then for the others, for x2 and x3, it's going to be 0. So this way here. And of course, this is just defining first basis functions, but you see the whole thing. I mean, it's the same thing for x2. It's just that it's going to be 1 here for x2 and 0 for x1 and x3. And the third one is going to be 1 for x3 and 0 for x1 and x2. So out of this, we sort of should be able to see logically what we need to change here in order to produce this. So I'm going to jump into code, do clear, and I'm going to create sims. I'm going to create symbolic variables. I need x, I need x1, x2, and x3 because, well, I need them. And I'm going to now create my A matrix. So I have 1, and then I have x1 and x1 squared. So 1, x1, and then x1 squared. And then I have 1 x2 x2 squared. 1 x2 x2 squared. And 1 x3 x3 squared. So this is my A matrix. And now I need to have my my identity matrix here, but this time it's going to be I3 because it's a 3 by 3 thing. So this is my A matrix and my I matrix. Perfect. And I get my C matrix here. I do A backslash I, and bam, I get this horrific expression. I can try to simplify it. It's not gonna do much use though. It's just going to simplify a little bit for me. Never mind, I don't really care about C anyways. I care about phi. So phi is going to be, I can actually call this, yeah, never mind, I'll call it phi. So phi is going to be what? Well, I have 1 x squared, and then I multiply this by c. And these are my basis functions. This looks horrible. Let's try to simplify this at least. So simplify. Usually simplify helps when you do a mathematical operation like this. It's not going to automatically simplify it for you. So there we go. This looks sort of more easy. Nice. So in order to really look at phi here, we can actually transpose it. So I'm not gonna transpose it and then declare it itself. I'm just gonna transpose it for readability's sake. So this is the way I want to write it because it's kind of nice. And this is actually exactly what I have written in the lecture notes, which you have previously used in the PDF files. This is what I did. So you have phi, perfect. What do we do with this? Well, we can evaluate this now for x1, x2, and x3. So let's do that. Let's do that and let's visualize it. So really, I'm going to show you a different method of creating this into a function. So I'm going to do capital P phi here, and then I'm going to wrap this in MATLAB function like this. Take note of this F here, and I'm going to just throw this into phi here. Throw phi into that function. So I get this thing. It looks really weird because it's a long thing, like it's a vector and stuff. But note here we have now, this is a different notation style in MATLAB. These guys are faster than the symbolic stuff, and you don't really need to have the symbolic toolbox to use these types of functions. So let's just create another function just to show you the thing. So we can do phi f is equal to, and then do at, and then the variable which this is going to depend on. And this variable doesn't even need to be symbolically declared, so I can do whatever. I can do ASD here, and then just do ASD plus 4. And if I run this, I get this function here, and I can use this now. I can use it this way, so I can put 2 here, and then it's gonna give me output, right? And this is called, well, it's the data type is function handle, but it's called an anonymous function. Don't ask me why. Anyhow, we can convert symbolic functions to these function handles using MATLAB function. And of course we can convert this back to symbolic function by just wrapping this guy back into sim. And so we have a way of going backwards and forwards here. So why am I using MATLAB function here? Well, I can just do phi, and I can say, all right, x is going to be my symbolic x, and then x1 is going to be 0, x2 is going to be 0.5, and x3 is going to be 1. And I get back this guy here, which I sort of have shown you earlier. And I can, I can change my element to whatever I want here. So it's sort of a nice way of using this. And it's also really easy to copy. You can just go in here, copy output, and paste it, and bam, you have this thing. So it's yeah, I don't know. I just prefer this guy to this stuff. So this is sort of horrible to copy into. Hey, this wasn't really horrible. This works. Never mind. I never tried it. All right. So you have different ways of doing things now. Use whichever you prefer. Right. So we have this thing here. Let's yeah. Remember, I told you you can always do a sanity check if this works. So I'm gonna call this phi again, like so, and I'm gonna evaluate this. So I'm gonna say that, all right, I have, I want to evaluate. Let's call this as a function like so. Can I get away with that? Yes, I can. Perfect. So I'm gonna evaluate this at 0, and I should be able to get 1 back exactly. And I'm gonna evaluate this at 0.5, and I'm going to evaluate this at 1. So I get back, so phi1 is going to be 1 in its own, I get the same property back as I used the definition for. So that's perfect. That works. So phi1 is 1 in its own node and 0 in the others. Phi2 is 1 in its own node and 0 in the others, and phi3 is 1 in its own node and 0 in the others. Perfect. The sanity check works. I can get rid of it. And let's plot this guy now. So I'm just going to go ahead and copy all of this stuff here, down here. And what do I need to change? Well, I'm still plotting this from 0 to 1, so that's okay. Line width can be 2, fine. Setting the font angle to italic, font name to times, font size to 16. Xticks is going from 0 to 1. Those are my xticks. Well, I should actually insert 0.5 in between here, and I should call the third one x3, like so. For my yticks, I can just leave them at 0 and 1. That's okay. And now I have, of course, a third thing here. Oops. There we go. Just set this to 3, and I can run this, and I'll see what I'll get. And there we go. So I get this beautiful quadratic thing. It's almost art, and this is very, very common. You will see this in different textbooks and whatnot. Now, for this lecture, I've actually put that in a problem that you will create a quadratic basic, not quadratic, a cubic basis function, right? So cubic means, well, C4 x cubed. And the rest you need to figure out yourself. So it follows the same logic, shouldn't really be hard. But yeah, so look at this video, try to figure out how to do it, make a nice plot like this. And yeah, this is a general way of creating basis functions for any polynomial order, really. So yeah, so we will use the same method of creating basis functions 2 and in 3 dimensions. Well, maybe not 3 dimensions because we're not gonna use them, but definitely in 2 dimensions. I will see you in the next video. Bye.